This is 16.6 mass, center of mass. So the idea here is using integration, we can calculate mass, we can calculate centers of mass given mass densities. Let's just do the one variable calculus version first. We have a interval from A to B. If it just has a mass density of 1, then just 1 everywhere, then the mass is going to be 1 dx, and it's just going to be b minus a. All right. So the interesting things come when you have mass density, which means you have a, for example, a rod of some material. It has length b minus a, right? And maybe certain parts are more dense than other parts, and so the mass is not uniform anymore, right? So the mass density, how dense the material is at each point, can be described as a function. We're going to call it rho of x, not to be confused with the rho from spherical coordinates, but this is a traditional letter that's used. In that case, the mass is going to be integral a to b rho of x dx. All right. Okay, so it makes sense that it's an integral because in a way, you're adding up at each point. In a way, you can think of it like at each point, this rod has some sort of mass, right? Has some amount of mass. And if you want the mass of the entire object, you're adding up the mass at every point. And what is adding up at every point? It's doing an integral. All right. Okay. Center of mass. So center of mass, the concept is relatively straightforward, right? We have a rod. It has perhaps some interesting mass density, heavies, dense in some places, not so dense in other places. The question is if you want to balance this object, right, so that it doesn't tip over on, let's say, a pin or something, then where should you put that pin? All right. Another way to say it is it's an average. All right. So I think that's probably the best description. So let's do it first with a mass density just 1 everywhere, right? So in other words, rho of x is equal to 1. Okay, so the center of mass is, one way to say it is it's an average of your x coordinate. All right, so average x value. All right, so it's going to be integral x dx a to b, and then we have to divide by the mass. All right. Let me write the mass like this. Divide by the mass. A to b 1 dx. All right. So this is my mass, total mass. Right? Just like if you're calculating average of 100 students' exams, right? You need to divide by the total number, right? And up here, right, we're integrating over x because we're looking for the average x value, right? Okay, and if we actually did this integral, we'll see that we get exactly what we expect. So this is going to be, the top is going to be 1/2 x squared from a to b. The bottom is just going to be b minus a. And so that's going to be 1/2 b squared minus a squared over b minus a. But that's 1/2 b minus a times b plus a over b minus a. And so that's 1/2 b plus a, which is exactly the midpoint between a and b. All right. So it's exactly this average x value, in a way, is exactly the concept of center of mass that we should use. all right? So we wanted to go through this because, of course, if you have different mass densities, it's literally the same formulas, right? So generally, right, you're again looking for the average x coordinate. So x dx, a to b. But now you have a mass density. Let me put it like this, rho of x. Okay. And the way you can think of this is you're now thinking about a weighted average, right? So some parts of your rod, if you're talking about physical mass, some parts of your rod count more than other parts of your rod. So you need to account for that, and that's what the rho does for you. All right, both in kind of the average portion of this, or the kind of the integral, the x integral portion and the mass integral. Just like if you want to calculate your course grade, right? Your final exam is worth more than a particular homework, right? So you have to weight that with a value, and that's what rho does. Okay. All right. So this is for a simple rod, right? A to B in 1 dimensions, but we can just easily extend this up into 2 or 3 or any number of dimensions in 2D, right? How do you do the mass? Well, if you have a mass density now, it's going to depend on 2 variables because you have a 2-dimensional object, right? Maybe a flat plate or something. So maybe you want to find the mass of a flat plate. And perhaps it's more dense on this side than on that side or something like that, right? So it has a mass density, perhaps that's more interesting than just 1. So what would the formula for the mass be? Well, literally the same idea. So rho x comma y, and then I'm not going to write dy dx, dA, and then over our region R, right? So this is our region, okay? All right. So how do you do the integral? Is just the integral, you just use integral techniques, right? So the only thing new in this section is basically these formulas for mass and center of mass. Okay, so this gives me my total mass. And of course, if we just want a uniform object made of a uniform material, the rho would just be 1, constant function 1. All right. Okay, what about center of mass? Well, things are a little more complicated than the rod situation, but still not too bad because we have 2 coordinates, so we expect the center of mass to, in a way, be the average x value and the average comma the average y, right? So the center of mass should be something like this. X rho, I'm just going to write it like that, over 1 dA. Oh, sorry, rho dA. Right, so this is the average, this left-hand side here is the average x in a way. And then on the right-hand side here, this is the average y. So this would be the coordinates of the center of mass. Okay, so let me put this in quotes, average x, average y. And when I say average, again, I mean weighted average, weighted by rho, right? Because some portions of this disk are more important, or of this flat plate are more important than other regions. Okay, 3 dimensions, well, you can probably guess. Your mass is going to be, well, your rho is going to be 3-dimensional, right? So we're talking about the mass of actual, in a way, a physical object in the real world. Different densities in different places. The mass is going to be triple integral over our region, so call this d, rho, and then dv. Okay. And of course, center of mass is going to be triple integral x rho dv, comma, I guess I should put down here, and this is just my total mass, y rho dv, z rho dv, as you expect. Okay, so the question is, how do you find center of masses of particular objects? Just set up these integrals, do them using the techniques we've learned from 16.1 to 16.5, and that's it. That's pretty much it for 16.6.